1 times x minus 7. Let me do this the long way. The long way would involve multiplying out the x plus 3 and the x plus 1. If I do that, we'll have x squared plus 4x plus 3 times x minus 7. Let's keep going. I'll multiply by the 2/3 last. X squared times x is x cubed. X squared times negative 7 is negative 7x squared. 4x times x is 4x squared. Then negative 28x plus 3x minus 21. You could do that with a large box if you wanted to. Clean this up. X cubed. I have negative 7x squared and positive 4x squared. That's negative 3x squared. Negative 28x plus 3x is negative 25x minus 21. Let's distribute the 2/3 through. 2/3 times x cubed is 2/3 x cubed. 2/3 times negative 3x squared is negative 2x squared. 2/3 times negative 25x is negative 50 over 3x. 2/3 times negative 21 is negative 14. The question asked for the constant term. There it is. The question also asked for the leading coefficient. There it is. Okay. This is an example of going a very long way to determine the constant term and the leading coefficient. The much easier way would have been, let's examine our original factored version. Where does the leading coefficient come from? The leading coefficient comes from right here. So the leading coefficient is this 2/3. The constant term, well, the constant term, if we look at our table of values, we were given the point 0, negative 14. That's the y-intercept for the polynomial. If that's the y-intercept, the negative 14 from the point 0, negative 14 is the constant term. That would have been a much more efficient method for finding the leading coefficient in the constant term. But our brute force method works as well. You always have options. All right, we're going to do one more problem before we wrap this up. In this third example, we're given a polynomial function. We want to first write f of x in factored form, and then second, we want to sketch a graph of the polynomial function. So we actually have several skills that we're going over in this video. Part A, I want to rewrite f of x in factored form. Well, we know that f of x is the polynomial 2x to the fourth plus x cubed minus 18x squared minus 9x. This polynomial has 1, 2, 3, 4 terms. If I want to factor an expression that has 4 terms, usually what we do, and it doesn't always work, but sometimes it does, is we split the polynomial into groups of 2. We look at common factors on the first half, common factors in the second half. Let's see, 2x to the fourth plus x cubed. I see a common factor of x cubed, leaving me 2x plus 1. Over here, I have a common factor of negative 9x. When I pull that out, it leaves me 2x plus 1. X cubed times 2x plus 1 minus 9x times 2x plus 1 is the same thing as saying x cubed minus 9x times 2x plus 1. That's good. This factor over here is linear, degree 1, so I don't expect any more factoring. However, the x cubed minus 9x is cubic, and if we're clever, I can actually see there's some more factoring to be done in here. X cubed minus 9x, there's a common factor of x that I can factor out. That would leave me x squared minus 9 times 2x plus 1. This x squared minus 9 is a difference of squares. Since it's a difference of squares, I can factor that as x plus 3 times x minus 3. So my original polynomial, f of x, can be rewritten as x times x plus 3 times x minus 3 times 2x plus 1. That's been written in factored form. Now, in part B, we want to sketch the graph of the polynomial function. And this is a whole other skill that is getting developed. You probably spent a day or two in pre-calculus taking polynomials written in factored form to actually generate the graph of the polynomial. In order to do this, we're going to find the roots. So the first thing is we're going to find the roots. We're going to find the roots. After we have found the roots, we're going to use the number line test to determine the sign of the polynomial at all of these points that are not the roots. And then the third is we're going to sketch the graph. Well, to do all of that work, I definitely need some more paper. So here we go. For f of x equals x times x plus 3 times x minus 3 times 2x plus 1, for the roots, we're just going to go straight across. What would make this factor over here equal 0? X equals 0. Check. What would make the factor x plus 3 equal 0? Well, that's x equals negative 3. What makes the factor x minus 3 equal 0? That's x equals 3. And what makes the factor 2x plus 1 equal 0? That'll be x equals negative 1/2. Those are my roots. Second, we do our number line test. So for our number line test, here's f of x. We have 4 distinct roots. We have 0. We have negative 1/2. We have negative 3 and positive 3. I know at each of these points the original function is equal to 0. Now what I don't know, and we're gonna work to figure this out right now, is what is the sign of the function before we get to negative 3? Is the function positive, meaning that we're above the x-axis, or is it negative, meaning that we're below the x-axis? What about in the interval negative 3 to negative 1/2? What about between negative 1/2 and 0? Between 0 and 3? After 3? To do this, what we do is we select test points in each interval. So for example, x equals negative 4 would be a test value in this interval. You don't have to use negative 4. You could use any factor, any value that you want to the left of negative 3, but I'm going to choose negative 4. Between negative 3 and negative 1/2, let's say negative 2. Between negative 1/2 and 0, well, there we're going to be stuck with a fraction. We'll have to use negative 1/4 maybe. Between 0 and 3, I'm going to use x equals 1. And to the right of 3, I'm going to say x equals 5. Those are my values. For each of those values, I'm going to plug those values into the original function. F of x equals x times x plus 3 times x minus 3 times 2x plus 1. And we're going to pay attention to the sign. If x equals negative 4, then x here is negative. Negative 4 plus 3 is negative. Negative 4 minus 3 is negative. 2 times negative 4 is negative 8, plus 1 is negative. Negative times negative times negative times negative is a positive answer. So I would expect that for any value of x that I select to the left of negative 3, my function will be positive, meaning above the x-axis. We're going to do the same thing for x equals -2. The first factor is negative, the second is positive, the third is negative, the last one negative. Multiply it all out. Negative times positive times negative is negative. So we're going to be negative in between -3 and -1/2. Plug in -1/4. Negative. -1/4 plus 3, positive. -1/4 minus 3, negative. 2 times -1/4 is -1/2, plus 1, positive. Negative times positive times negative times positive is positive. Now we try x equals 1. We can do that one pretty quickly. Positive, positive, negative, positive. Positive times positive times negative is negative. Lastly, x equals 5. Scoot that up. Plug it in. Positive, 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 positive. Multiply it all together, we have positive. So my function, the way we're going to look at this number line test, the function is positive above the x-axis, hits a root, drops below the x-axis, hits another root at -1/2, is above the x-axis, hits another root, drops below the x-axis, hits another root, pops up above the x-axis. A quick sketch, here it comes, and then we'll be done. We have -3, -1/2, 0, +3. Each of these points represents a root, so my function has to pass through those points. My function is above the x-axis before we hit -3, drops below the x-axis between -3 and -1/2, is up above the x-axis between 1/2 and 0, is below the x-axis between 0 and 3, and then is above the x-axis after 3. There we go. And a lot of that information we had earlier. If we look back to how the original polynomial function was given to us, we had f of x is 2x to the 4th plus x cubed minus 18x squared minus 9x. The degree is 4, which is even. That tells me that the tails must be doing the same thing. They're both pointing up or they're both pointing down. The leading coefficient was greater than 0. It was +2, so both tails are pointing up. Check. The constant term, well, let's see. There was no constant term. The constant term is 0, so my y-intercept is actually here at the origin. Everything fits together. It has to. This is the beauty of mathematics. Well, congratulations. You survived the video on polynomials in factored form and in standard form. In a little bit, I'm going to create another video on analyzing polynomial functions with the graphing calculator. I hope this was helpful.